Okay, so this is chapter 26, the fluid, electrolyte, and acid-base balance chapter. This is kind of like a continuation of the urinary system chapter. And you're going to see a lot of overlap. So we're going to talk about a lot of things in this chapter like aldosterone and ADH, which we've already seen before. So I may go through some of this stuff very quickly, but that's because we've already covered it in the last chapter. So, and then again, you have your notes to go back to and reference. Memorize your percentages of body water content. For infants, it's about 73%. For adult males, it's about 60%. And for adult females, about 50%. Females have more fat and less skeletal muscle because men have testosterone. And so skeletal muscle is much more hydrated than fat. Fat's about 20% water, whereas skeletal muscle is about 70%. So that's where men get that higher percentage of body water. As you age, your body water declines. It's about 45% in old age. When we look at the total water in the body, a lot of people would think, well, most of the water's in your blood, right? Well, actually, most of the water is in your cells. The intracellular fluid makes up 2/3 of all your body's water. And then your plasma, which is your blood fluid, your interstitial fluid, and a number of other fluids make up your extracellular fluid, which is all together about 1/3. So some other fluids are like the lymph, the cerebrospinal fluid, fluid in the eyes, things like that. Now memorize the major electrolytes in the extracellular fluid and intracellular fluid. We know that cations are positive. If you ever forget, the T looks like a positive sign, right? So cations are positive ions and anions are negative ions. The major cation in the extracellular fluid is sodium, and the major anion is chloride. In the intracellular fluid, the major cation is potassium, and the major anion is hydrogen phosphate. So go ahead and memorize those. And we should know this a little bit from 201 with the muscle chapter. Sodium mainly lives outside the cell, potassium inside the cell, so that gives us our cations at least. So on this slide, I want you to focus on, we talked a little bit last chapter about osmolality or osmolarity, which is the ability to draw water to it. And so if we increase, now we talk about extracellular fluid, a lot of times we're talking about the blood. And so if we increase the extracellular fluid osmolality, that means the concentration of the blood has increased. So what's going to happen? Well, water always moves to the more concentrated side. So if it's more concentrated outside the cell in the blood, then water is going to leave the cell. If you have a decreased osmolality in the extracellular fluid, well, then water goes into the cell. It makes sense because water is always, again, going to move to the side of higher osmolality. Now, your water intake should equal your water output, which is about 2,500 milliliters a day. And that's going to vary from individual to individual. But there's a number of ways we lose water. And a lot of people, if we ask, well, how much do you lose in urine? People might say 80, 90%, but it's about 60%, which is still the major component of water loss. But we have a number of other areas where we lose water. There's these insensible water losses, which is through the skin and lungs. And then there's perspiration, which is sweating, and feces. We lose some water as well. Now you say skin and perspiration is not the same thing. Well, no, perspiration is sweating. We can sense that, right? We can see it, we can feel it. The insensible loss through the skin is evaporation. Now, if we have a rise in plasma osmolality, what's going to happen? Well, we have to think about this. If the blood becomes more concentrated, right? The osmolality means it's a greater concentration of solutes if it's rising. It's going to stimulate thirst. And what else are we going to do? Well, we want to put more water in the blood. How do we do that? Well, we have that hormone called ADH, antidiuretic hormone, that prevents diuresis. Well, that means it prevents the formation of urine. Well, if we're doing that, where's the water going? Well, we know that ADH increases the reabsorption of water. We saw that in the last chapter. So if we have higher osmolality, we'll release ADH, pulling more water into the blood. Again, water always wants to dilute the more concentrated side. If we have a decrease in plasma osmolality, then there's going to be an inhibition of thirst, and we're going to inhibit ADH as well, because if the osmolality is low, okay, then essentially what we want to do is we want to get rid of some water, okay? So blocking the thing that blocks diuresis is what we want to do in that case. Now your hypothalamus has the control over the thirst in your body, so it has that thirst center. And that's going to be the driving force for, water intake. And so what is going to stimulate this hypothalamic thirst center? Well, there's a number of things that can do that. If we increase the plasma osmolality, which we mentioned on previous slides, but only by 1 or 2%. So it doesn't have to be a lot of shift, but if we increase that concentration of the blood, it stimulates the thirst reflex, so we will ingest more water, absorb more water, and decrease the osmolality back down to normal. Another thing that would do it is dry mouth. We'll see that with sympathetic nervous system responses. Decreased blood volume or blood pressure, regardless of what the reasons are, that's going to want to drive more water into the blood. So again, thirst reflex gets stimulated. Angiotensin II, we saw that increasing or activating the hypothalamic thirst center was one of the effects of angiotensin II. And so those are our causes for activating the hypothalamic thirst center. Now, when you drink water, it creates an inhibition of the thirst reflex. Satisfying, basically, this inhibitory feedback comes from, you relieve the dry mouth, you activate, the stomach and intestinal stretch receptors, and your body's like, ooh, I'm good. But when it gets to the intestines and we start to absorb the water, let's say it's not water, let's say you're thirsty and you drink soda. Well, that has a high osmolality, so we don't absorb a lot of water from things like soda. And so what's going to happen is it's going to re-trigger the thirst reflex once your body realizes, hey, this is not water. Because when you have a thirst reflex, it's specifically asking for water, right? Now, obligatory water losses are losses that you have no control over, that you have to lose a certain amount of water per day. And it's going to be the evaporation from the lungs and from the skin. Okay, so from our breathing, we lose some water, and from the skin, the evaporation in the skin will lose water. We'll also lose some from feces and about 500 milliliters from urine as well. You can survive approximately 3 days without any water. You can survive without food for longer than that, but without water, it's approximately 3 days. Now, this is similar to things we've talked about before. If we decrease ADH, now we're not talking about blood in this instance, we're talking about what happens to urine. Well, if we decrease ADH, well, ADH blocks the formation of urine, it actually concentrates urine. So if we decrease it, it's going to dilute the urine, right? If we increase ADH, that means we're going to block diuresis, and that means we're going to pull more water back into the blood, leaving less in the tubules, and that's going to concentrate urine. Other factors that you see that will trigger ADH release. Now think about this. Anything that causes like dehydration or water losses, so we can look at things like intense sweating, vomiting, diarrhea, severe blood loss, prolonged fevers or burns. These are things that will stimulate the release of ADH so we can draw more water into the blood and prevent water losses. Now this slide specifically talks about dehydration. You see, very similar to the last slide, things that would stimulate ADH. Hemorrhage, burns, vomiting, diarrhea, sweating, and other things like water deprivation, diuretic abuse, some endocrine disturbances. So these are things that could lead to dehydration. And just be familiar also with the term oliguria. It's one of the symptoms here, decreased production of urine. A lot of people don't know what that word means, so it's important to know. And now one of the really important things here, the dangers of dehydration, it's not just loss of electrolytes and confusion and weight loss and things like that. Hypovolemic shock, because really when we're losing water, we're losing it from the body, but what is the blood primarily made up of? The plasma is primarily made up of water. So when we lose water from the body, we lose it from the plasma, and that makes the volume of the blood go down, which crashes the blood pressure as well, which could lead to that hypovolemic shock. Now, could we get too much water? Yes. Hypotonic hydration, which is also called cellular overhydration, which is also called water intoxication. Of course, we need 3 names for the same thing, right? Well, this water intoxication can occur primarily from one of 2 reasons. Either renal insufficiency, with some type of kidney disease where you're unable to, flush that water out, or rapid excess water ingestion, so ingesting a lot of water in a very short period of time. This is not saying if you drink a gallon, 1.5 gallons, or even 2 a day, which is a lot of water, 2 a day, but if we drink that much, you're nowhere near in danger of having this water intoxication unless you're ingesting that water in a very small window. And usually it's even higher amounts than that. Unless you have a renal disease, then even normal high amounts could be problematic. Now let's talk about edema. Edema is a fluid accumulation in the interstitial space, right? The space between cells. And so there's a number of things, and we'll go through some causes for this, for this edema. So anything that increases the fluid out of the blood or hinders the return back into the blood, that will cause edema. So let's look at some examples here. Hypertension, high blood pressure, that'll force more fluid out of the capillaries into the interstitial space. again, creating a burden on draining that fluid out, and so fluid may accumulate in the interstitial space. If there's chemicals, inflammatory chemicals that increase capillary permeability, then we may get more fluid in the interstitial space. Incompetent venous valves could be a problem as well, blood vessel blockage, and then even congestive heart failure. So we're going to have an increased blood volume, which is going to force more fluid out into the interstitial space. Now also, hindering fluid return can occur with an imbalance in what's called colloid osmotic pressure. What is this? It's the osmotic pressure exerted by the proteins in the blood. So if you have low blood protein, so hypoproteinemia, this is a decreased plasma proteins in the blood, so they serve as electrolytes, keeping the fluid in there. And so if they decrease, then fluid will leak out of the blood, and you'll end up with, again, fluid in that interstitial space. Some causes for this, protein malnutrition, liver disease could cause this, and even the autoimmune disease that affects the glomerulus called glomerulonephritis can cause this as well. All right, so also if we learned in the lymph system that the lymphatic capillaries drain the interstitial space. So if you have blocked lymph vessels or you have surgically removed lymph vessels, then you've lost those drainage, those drainage pipes, right? Those lymphatic capillary or vessels that are going to drain the interstitial space. So this can again result, if we're draining less, it can result in accumulation of fluid in the interstitial space, again causing that edema. Now, electrolytes are usually salts, acids, and bases, but they usually refer to salt balance. And so we'll see things like neuromuscular excitability, secretory activity, membrane permeability, and controlling fluid movements as functions of these electrolytes. And we'll talk a little bit more detail as we go through the individual electrolytes. So sodium is the primary electrolyte driving fluid movement. Your textbook talks about how it holds a central position in fluid and electrolyte balance. It actually accounts for 90 to 95% of all the solutes in the extracellular fluid, and it's the most abundant cation, as we said before, in the extracellular fluid. Now, it's the only cation that exerts significant osmotic pressure. And so this primary electrolyte driving fluid movement, the sodium, is going to be the key, right? And that's why when we have something like aldosterone, which we'll talk about, that's going to increase sodium reabsorption, it's going to help drive water back into the blood along with the sodium. Now, let's look at the bottom two bullet points here. Sodium leaks into the cells and is pumped out against its electrochemical gradient. What does that mean? Well, sodium wants to go into the cell because it primarily lives outside the cell, which means its concentration gradient and its electrical gradient, because the inside of the cell is negative, it wants to pull sodium into the cell. Well, we have to use the sodium-potassium pumps to pump sodium out of the cell against its electrochemical gradient, okay? We saw that in the muscle chapter in detail, as well as the nerve chapter. Now, sodium content can change, but the extracellular fluid concentration of sodium remains stable due to osmosis. What does this mean? This means if I take sodium from one side of the membrane and move it to the other, that should make it more concentrated, but it doesn't, because water also follows through osmosis. Because what we did when we moved the sodium over is we increased the osmolality on that side, pulling water over with it, so the concentrations on each side remain stable. Now this slide should be a good review of things we've talked about before. And add a little bit to it. So we're going to absorb about 65% of our sodium in the proximal convoluted tubules. We had mentioned that. We said 65% of water and sodium in the proximal convoluted tubules gets reabsorbed. Now, going up the loop of Henle, we said we'll reabsorb some electrolytes, and sodium, about 25% of the sodium. Now, what are we talking about? Well, let's say I squeeze out 100 sodiums from the glomerulus in glomerular filtration. Well, 65 of those go back into the blood in the proximal convoluted tubules. 25 go back in the ascending loop of Henle. Okay. Now let's go down to this second bullet point here for a second. Aldosterone increases the reabsorption of sodium. We know this. Where does it do its action? Well, from the last chapter, we know that in the distal convoluted tubule and the collecting duct, that's where aldosterone increases the reabsorption of sodium. So most of that remaining 10% go back into the blood if aldosterone is secreted. Now, let's go back up a second. Sodium is never secreted into filtrate. So what we're saying is if I squeezed out 100 sodium in glomerular filtration into the tubules, obviously I'm pulling 65% 25% back in the proximal convoluted tubules, 25% in the loop of Henle. I'm never secreting any into the filtrate. In other words, I'm not adding any more than those 100 from glomerular filtration. So we're never going, so secretion, remember, is blood to tubules. We're never putting sodium from the blood into the tubules after we pass the glomerulus and have that glomerular filtration, okay? Now, what else? We know sodium and potassium move in opposite directions. So we know that not only is the function of aldosterone to increase the reabsorption of sodium, but it also increases the secretion of potassium, okay? And remember, water is going to follow sodium. So as we increase sodium in the urine, we increase water loss. So if we increase sodium in the blood, we increase water gain into the blood or prevent water loss. Now, we've already talked a lot about the renin-angiotensin mechanism and the functions of angiotensin, so I'm not going to recover those. But I do want to point something out here, that there's, and this goes all the way back to the endocrine chapter, there's a couple of things that will stimulate the release of aldosterone. So low blood pressure will cause the renin-angiotensin system to, cascade to happen, which causes angiotensin 2 to be produced, and that angiotensin 2 will, increase the blood pressure, okay? And so one of the things what ways it does it is it causes the release of aldosterone. So that's one trigger. Another trigger for aldosterone release is if we have elevated levels of potassium in the extracellular fluid, because what else does aldosterone do? Well, it causes secretion of potassium. So if the levels in the blood are too high, we can pull sodiums in, and for every sodium we pull in by reabsorption, we secrete a potassium. So that's a second trigger for aldosterone release. Now, if we look at atrial natriuretic peptide, this is literally like the opposite of the renin-angiotensin mechanism. If we look at it, what does it do? Well, we said before that it decreases sodium reabsorption. That looks like it's just like, the opposite of aldosterone. But look what it does. It's going to decrease ADH. It's going to decrease renin. It's going to decrease aldosterone. All of those things are produced when we have, in reverse, right? When we're doing this renin-angiotensin mechanism. It's going to increase excretion of sodium. And we know that angiotensin 2 is a vasoconstrictor. Well, ANP is the opposite. It's a vasodilator. And it blocks angiotensin 2, which means it not only directly acts as a vasodilator, but by blocking the vasoconstrictor angiotensin 2, it indirectly vasodilates as well. So what does it do? ANP is going to decrease blood pressure and decrease blood volume. Okay, so by decreasing the volume, we're decreasing the pressure, but also by vasodilating systemically, we're short-term decreasing the pressure. So again, if you know the renin-angiotensin mechanism, just everything opposite would be what atrial natriuretic peptide does. Some other hormones with effects on sodium, we have estrogen that increases sodium chloride reabsorption, very similar to aldosterone. So when a female has a menstrual cycle or pregnancy, it increases water retention. Progesterone is the opposite. It decreases sodium reabsorption and it blocks aldosterone, so it promotes sodium losses. Cortisol is going to increase sodium reabsorption and also promote edema. Now, the key things I want you to focus on this slide really are hyperkalemia means too much potassium in the blood. Hypokalemia means too little potassium in the blood. Kalium, remember, is the Latin name for potassium. That's why it's K. Either one, too much or too little, is going to disrupt electrical activity of the heart, and it can lead to death. Another thing to know is that potassium is part of your body's buffer system. So it shifts in opposite directions of sodium, yes, but it also shifts in opposite directions of hydrogen ions, which is another cation. And so, so let's say this: if extracellular potassium levels rise, okay, with acidosis, potassium leaves as the hydrogen is entering the cell. Extracellular potassium levels fall with alkalosis as potassium enters and hydrogen leaves the cell in that case. So essentially really what I want you to get from this without getting too confused is that potassium and hydrogen are moving in opposite directions. Now, we already talked about how aldosterone affects potassium, right? It causes potassium secretion. As we reabsorb a sodium, we secrete a potassium. And we know that the high levels of extracellular potassium are actually a trigger for aldosterone release. Okay, let's talk about calcium. Calcium is important for blood clotting, membrane permeability, secretory activities, and neuromuscular excitability, which is the most important, right? The nerve conduction, muscle contraction, we saw detail on that in chapter 9 when we did Anatomy 201, right? Anatomy 1. And so 99% of your body's calcium is found in the bones. We talked about PTH and that how it regulates blood calcium. So when you get a blood calcium test, it's really just checking to see if PTH is working properly, right? Making sure we increase blood calcium when needed and negative feedback shut off PTH when we don't. A bone scan is really the only way to assess calcium status because, again, 99% of your calcium is found in the bones. Now, if we have hypocalcemia, what does that mean? Low calcium in the blood. That's going to increase excitability and cause muscle tetany, which is that sustained contraction of the muscle. If we have hypercalcemia, too much calcium in the blood, it's going to inhibit the neurons and muscle cells, and this can lead to heart arrhythmias. Okay. Now, if you remember from the endocrine chapter that parathyroid hormone is the primary controller of calcium balance. When calcium drops low, PTH or parathyroid hormone gets released. It raises calcium. And then when we have enough blood calcium, we get a negative feedback that shuts off parathyroid hormone release. To review the three mechanisms that PTH uses, first off, PTH has one goal, raise blood calcium. That is it. But it does it three different ways. It does it by activating osteoclasts to break down the bone, which is made up primarily of hydroxyapatite, which is calcium and phosphorus, so releasing calcium into the blood. It's going to increase reabsorption of calcium, okay, and that's going to happen, remember, at the distal convoluted tubule and collecting duct. And in the small intestines, it's actually going to increase absorption of calcium, but it's going to do this indirectly because it's going to help activate vitamin D. And vitamin D is going to increase the calcium absorption. So these are three ways that we're going to increase calcium absorption into the, or calcium, I should say calcium levels in the blood, reabsorption, absorption, and breaking down the bone to put calcium in there. Now, if PTH is released, you're going to actually reabsorb 98% of the calcium that got squeezed out in glomerular filtration. If extracellular calcium levels are normal, PTH secretion gets inhibited by that negative feedback. Now, there is another hormone released by the thyroid called calcitonin, and an easy way to remember it is it puts calcium in the bone. And so calcitonin is the antagonist to PTH. It only has a minor effect because usually we have low blood calcium, PTH gets released. When we have enough, we shut it off, and that usually regulates blood calcium levels. But if blood calcium levels were to rise too high, then we would release calcitonin that would shuttle the calcium into the bones. Okay, another electrolyte, chloride. As we said, it's the major anion in the extracellular fluid. 99% of chloride is reabsorbed under normal pH conditions. If acidosis occurs, then we absorb less chloride ions. Remember, chloride is really important for things like HCl, right? We talked about that in the digestive chapter, that the parietal cells are going to secrete this substance called HCl. Well, the Cl part is chloride. So that takes care of the electrolyte portion. Let's talk about acid-base portion of this chapter. The normal physiological pH of blood is 7.35 to 7.45. If we drop under 7.35, that is considered acidosis or acidemia. I will always use the word acidosis, by the way, but in case you see it. And if we go above 7.45, it's alkalosis or alkalemia, and again, I will use alkalosis. Now, that is not, if we go below 7.35, that is not acidic chemically, but it is considered acidosis because your physiological normal is 7.35 to 7.45. Now, most hydrogen ions are produced by metabolism. Now, don't forget, our acidity has to do with hydrogen ions. We talked about that before. As hydrogen ions go up, acidity goes up, which means the pH goes down, right? So some ways that we produce it, breakdown of phosphorus-containing protein, which releases phosphoric acid. That's one way. Lactic acid, it gets produced from anaerobic glycolysis. Fatty acids, if we break them down for fuel, one of the byproducts are ketone bodies, and ketone bodies are acidic. And then hydrogen also gets liberated from carbon dioxide, or when carbon dioxide, I should say, is converted to bicarbonate. HCO3 is bicarbonate. Okay? Now, we have three buffer systems in the body. We have a chemical buffer system, we have a respiratory buffer system, and we've been exposed to these a little bit. And then we have a renal buffer system. This is the kidneys, and this is actually going to be the most powerful of the three. It's going to take a little bit longer. The chemical buffer system works all the time, and then the respiratory It takes just a couple minutes to work. And we talked about that as flushing carbon dioxide out or preserving carbon dioxide. So we'll cover each of these. Now, a principle, strong acids are going to dissociate completely in water, so they're going to have a big effect on pH. Why? Because they're releasing a lot more hydrogen ions. Weak acids, they release less hydrogen ions, so they only have a small shift. Strong bases, they're going to tie up lots of hydrogen ions, and weak bases tie up hydrogen ions more slowly. And so what we want to do when we're buffering with the chemical buffer system is we want to turn strong acids into weak acids and strong bases into weak bases. And this picture is just showing you like a strong acid like HCl giving lots of hydrogen ions, and then bicarbonate giving less hydrogen ions into the solution. Now we have three chemical buffer systems. You've already been exposed to the bicarbonate. We call it the bicarbonate carbonic acid buffer system. We also have a phosphate buffer system and then a protein buffer system. So let's cover each of the three and how they work. And it's going to have to do with either binding hydrogens and taking them out of the solution or releasing hydrogens into the solution. When we talk about the bicarbonate buffer system, we have bicarbonate and we have carbonic acid. Now, carbonic acid is a weak acid and it can release one hydrogen. And bicarbonate is a weak base that can bind one hydrogen. Okay, so every one bicarbonate we have will bind one hydrogen. Every one carbonic acid can release a hydrogen, and so it can change the pH just a bit, right? So we can use these as buffers to tie up hydrogens or to release hydrogens. Now, it works in the intracellular and the extracellular fluid, but it is the only important buffer in the extracellular fluid. So this slide talks about how one bicarbonate ties up a hydrogen and forms carbonic acid. And then if we have carbonic acid, it can dissociate and donate a hydrogen depending on what we need, right? If our solution, if we have a strong base, we're going to want to give hydrogens to that solution to basically lower the pH, right? If we have a strong acid, we're going to want to tie up those hydrogens to raise the pH. Okay, so a second buffer system is the phosphate buffer system. All the buffer systems work identical. They either tie up a hydrogen or they donate a hydrogen. In this, we have different components. We have dihydrogen phosphate, which is going to work as the weak acid that will donate a hydrogen. And monohydrogen phosphate will serve as the weak base that can tie up a hydrogen. Now, this is not really found abundantly in the plasma, so it's not really important in buffering plasma. It's going to be important in the urine and mainly in the intracellular fluid where phosphate concentrations are high. The protein buffer system, same thing. We're going to use an acid and a base. Now, the difference here is the protein molecule. Now, these are intracellular, so let's make sure we focus on that. That means they only work, these are intracellular proteins, so they only work inside the cell. They're the most plentiful buffers and the most powerful, but not in the extracellular fluid because they're intracellular proteins, okay? So they're most powerful overall, but only when we're comparing the intracellular because, again, if it's not working extracellularly, then it's not powerful outside the cell. Okay, but pound for pound, it's the most powerful buffer. Now, it's amphoteric. What does that mean? That means that there's an acid arm and a base arm. And so when we look at it, the carboxyl group, the COOH, is the weak acid group of the protein, and the amino group, the NH2, is going to be the weak base. So the weak base, the amino group, can bind a hydrogen, and the weak acid, COOH, can donate a hydrogen. So instead of having two different chemicals, we have a protein that has one group that's acid, one group that's base, and we can use either depending on what we need to buffer. Now, there's a limitation to chemical buffers. They don't eliminate the acids and bases, right? What they're doing is they're buffering, right, or making a strong acid a weak acid, making a strong base a weak base. Now, the lungs can eliminate carbonic acid by eliminating CO2. The kidneys also have ways to eliminate some of these things, and it is the most powerful of the three buffer systems. So it can get rid of phosphoric acid, lactic acids, the ketone bodies we mentioned before. And it will also do things, which is going to be the most powerful function of the kidneys, where it can renew chemical buffers or create chemical buffers, and so we'll talk about those in just a little bit. Let's review the respiratory buffer mechanism that we covered in the respiratory chapter. When we have high carbon dioxide in the blood, which is called hypercapnia, what's going to happen? It's going to result in acidosis. We said the carbon dioxide and hydrogen like to play together, right? So as carbon dioxide goes up, hydrogen goes up, and so it results in acidosis. How do we respond to that with our respiratory buffer system? Well, we need to flush the carbon dioxide out. If we lower the carbon dioxide, we lower the hydrogen. So rapid deep breathing is going to flush carbon dioxide out. It's going to lower hydrogen ion concentration, thereby lowering the acidity, right, and raising the pH back to normal. If we have a state of alkalosis, then we're going to slow shallow breathe to preserve carbon dioxide, which will thereby increase hydrogen ions, which will bring the pH back down from the alkalytic state. All right. Now, this is not talking about a buffer system. This is talking about when the respiratory system is impaired. So let's say we are at normal. We don't have high carbon dioxide that we need to fix or low carbon dioxide that we need to fix. We're at normal, but then there's a respiratory impairment that is causing us to go to the abnormal. So if we have something that causes hypoventilation, so a decreased ventilation, that's going to do what? Well, it's going to preserve carbon dioxide even though we don't need to. So carbon dioxide levels are going to rise, which means hydrogen ions are going to rise, and that results in respiratory acidosis. Hyperventilation, so we're at normal. Let's say you have a panic attack, you hyperventilate. What's it going to do? It's going to flush carbon dioxide out, and by flushing the carbon dioxide out, we lower the hydrogen ion concentration, which increases the pH, so we end up with respiratory alkalosis. Now remember, respiratory acidosis is if you have too much carbon dioxide in the blood. Respiratory alkalosis if you have too little carbon dioxide in the blood. Those are the causes. It's a carbon dioxide cause. If acidosis or alkalosis occurs for any other reason, then we call it metabolic. Okay, so the most important renal mechanisms are three for the kidneys: conserving or reabsorbing bicarbonate, generating new bicarbonate, or excreting bicarbonate. So if the first two, if we reabsorb, which means we're conserving bicarbonate, so we're putting more bicarbonate, remember reabsorption goes into the blood, we're putting more bicarbonate into the blood, right? That's increasing bicarbonate levels. If we generate new bicarbonate, we're putting more bicarbonate in the blood. Both of those things will affect acidity, will lower acidity, right? The third one, excreting bicarbonate, what does that do? Well, if you have alkalosis, then you want to excrete bicarbonate, right? To lower the amount of bicarbonate that can bind hydrogen, so you end up with more hydrogen, which means you raise the acidity, right? Getting the pH back down. So those are the most important. And I think we already mentioned that every one bicarbonate can bind to hydrogen, and so what we're doing is every time we increase bicarbonate by one, we decrease hydrogen by one. Every time we excrete a bicarbonate, right, then we're increasing hydrogen by one. So they're opposites. Now, I said respiratory acidosis and alkalosis has to do with a shift in carbon dioxide. If it's anything that causes acidosis or alkalosis outside of the shift in carbon dioxide, then it's called metabolic acidosis or alkalosis. So let's go through each of the four. Respiratory acidosis is the most common cause of acid-base imbalance of the four. And metabolic acidosis, we're going to see on the next slide, is the second most common cause. Now, what are causes of respiratory acidosis? Well, hypoventilation can result in respiratory acidosis, as we mentioned on a previous slide. When can this happen? Well, when a person is breathing shallowly, right? So gas exchange is hampered. We can have diseases like pneumonia, cystic fibrosis, or emphysema that could result in this hypoventilation, which would result in a respiratory acidosis. What about respiratory alkalosis? Well, hyperventilation, we mentioned, can result in respiratory alkalosis. Stress, anxiety attacks, panic attacks. It can also occur from infections, heart or lung disorders, bleeding, and even at high altitudes from the oxygen deficiency. So these are reasons you can have hyperventilation. That hyperventilation flushes carbon dioxide, lowers the hydrogen ion concentration, causing respiratory alkalosis. Metabolic acidosis is the second most common cause of acid-base imbalance. This is not all-inclusive. There's tons and tons of reasons. We'll look at a couple of reasons here. Ingestion of too much alcohol. Alcohol metabolizes to acetic acid. That raises the acidity level. Excessive loss of bicarbonate. Remember, every one loss of bicarbonate increases the hydrogen ions by one. So something like persistent diarrhea could cause that. Accumulation of lactic acid, like in lactic acidosis. Ketosis in a diabetic crisis where you're increasing the ketone bodies to the point of causing ketoacidosis. Starvation will do the same. Or even kidney failure. So these are things that could lead to metabolic acidosis. Metabolic alkalosis is not as common. This is rising blood pH, and bicarbonate causes can be vomiting, acid contents of the stomach, intake of excessive base, so taking too much antacids, constipation, which we can cause excessive reabsorption of bicarbonate. And so those are some reasons that would lead to metabolic alkalosis. Now, what happens if we have extreme changes in pH? If the blood pH drops below 6.8, it depresses the central nervous system, leads to coma and then death. If the pH rises above 7.8, it hyperexcites the nervous system, causing muscle tetany, nervousness, convulsions, but this can also lead to death, usually from respiratory arrest. So either extreme pH changes can lead to death. All right, our last slide. What is this saying? It's talking about the respiratory and renal compensatory mechanisms. What does this really mean? It means that if the respiratory system is impaired, the kidneys will try to help balance the acid-base imbalance caused by the respiratory dysfunction. If the kidneys are dysfunctional, the respiratory system will try to help counterbalance or balance the imbalances caused by the kidney dysfunction. So they're basically going to work, all the time for any acid-base imbalance. So they're going to work together to compensate for the other. If there's a respiratory problem, the kidneys compensate for it. If there's a kidney problem, the respiratory system compensates for that, as far as trying to regulate and control acid-base imbalances.